So hi everyone. First of all, uh, welcome. This is the mini lecture series that we'll be having. What the basic motivation was, huge lectures get very boring and tiring to hear, and you don't really get anything productive out of them. So what our motive is that we can provide some sort of introduction to a wide scope of topics which are practically used in the applications you might see every day, and some interesting topics as well. Uh, okay, am I audible, right? I am, right? Uh, so, uh,
Yes.
cool. So just some guidelines so the lecture can go smoothly. So everyone, we are recording this lecture so that we can uh, put it up on Facebook and YouTube later on. So if someone could not attend the lecture, they can see that then as well. Also, you can see if for reference. But yeah, apart from that, it would be great if everyone keeps mute during the lecture. We'll have a short Q&A after the lecture as well. So if you have some urgent question, you can put it up on chat, and other members can answer your questions at that time. But apart from that, we'll have a Q&A later on, so you can ask all your questions during that time. Uh, I think we can start now, and if anyone wants to join in, I'll admit them. Cool. Over to you, Kanav.
All right. So let's start.
Yeah,
Mohit?
hello. My name is Mohit, and the topic of this session is just to give you guys a really quick introduction to HTTP and how it differs from HTTPS. So, some necessary background. I just want to point out that all communications that take place across the network work on top of something called network sockets. So in order for two nodes in a network to communicate, they need to have a socket connection. And sockets are of two major types. You have stream sockets and you have datagram sockets. But for the sake of this discussion, we'll only be concerning ourselves with stream sockets. And the reason for that is stream sockets come with a lot of convenience. The actual communication takes place across several layers, but this level of abstraction and plus the convenience of stream sockets allows us to work with certain assumptions which simplify our life. For example, we can assume that every data packet we send will be safely received at the other end, and the order in which we send the data packets will be retained, so there won't be any kind of scrambling. With that out of the way, I also want to point out what a protocol actually is. So the way a socket connection works is all the communication, like all the data that goes across a socket connection, is basically in the form of a string or a byte sequence, which is more or less the same thing. So a protocol is just a bunch of rules that both the communicating parties agree upon that they use to package / format this data. So you know that just to make sure that whatever you're transmitting can be easily interpreted at the other side. HTTP is one such protocol, and here's what a typical HTTP request looks like. So you have headers and you have a body, and what the headers are just key value pairs, and they basically contain metadata about the request. For example, in the first line of the header contains the method of the request, which is post here, the route of the resource that you're requesting, and the version of HTTP that you're using. Then you have a bunch of other headers which specify some information. For example, user agent contains information about your OS and your browser. And the cookie header contains all the cookies that you have associated with that site. And then the final content that you want to send in that request is contained within the body. So unconventionally, after headers, you need to have two new line characters followed by the body, and the request ends with two more new line characters. And HTTP works on something called the request response model, which means that you need to request a resource before you receive back a response that contains that said resource. So response on the right side, you can see the response of this particular HTTP request, which looks pretty similar to the request itself, except that the first line contains the HTTP version and the status code. And the status code basically lets us know if there was any error with our request being processed and stuff. 200 means it was processed fine. And so in order to establish communication between two nodes, we need to make use of something called routing. So you have IP addresses on a network, which is what the TCP/IP protocol works on, and what IP and IPs are basically like virtual addresses. So these are just like numerical labels which act as virtual addresses of a device on a network. And then ARP, the address resolution protocol, is used to associate a physical device with its IP address. So that if you know the IP address of any other node on the same of any other device on the same network, you can form a link between them. You can form a link with them.
All right. Can you hear me?
Yes.
Yes. All right. So, so right now we only discuss about how HTTP works, right? So we know that all of the communication in HTTP happens in form of strings. So it is very reasonable to know that reasonable to judge that can be tapped. So if you it might be even possible to like if there are two people communicating over a wire using HTTP protocol. So the Oscar can easily just fetch the information out of it because he knows that there is nothing like there is nothing unknown to him. So this attack model is called a man in the middle attack. So where Alice and Bob are trying to communicate with each other, and Oscar tries to get the get the messages that both of them are exchanging. So the question is, can we just use encryption to prevent this attack? So suppose if Alice and Bob know each other beforehand, so they can exchange a secret key and then easily encrypt their messages, and they can just communicate safely. But we don't know everyone on the internet, so we need to devise a way of securely exchanging a common key, so which both of the parties know and can then use it to encrypt or decrypt their messages. So one such key exchange protocol is known as Diffie-Hellman protocol. So in this protocol, A and B agree on a set of numbers G and P, where G is called generator and P is a prime number. Obviously, these two number, not necessarily G, but P needs to be a very big prime number so that the security can make sense. So A and B both generate private numbers A and B, and calculate the modular exponential of G to their respective private numbers, and they send these two numbers to each other publicly. Please note that the values written in red denote public values, and in blue denotes the private value. So if Oscar is tapping all of the messages between these two parties, he would know G, P, and these two values, right? So when both of the parties receive these values, B receives this value, G raised to power A mod P, and A received raised to power B mod P. So when both of them receive, they raise the receive power to the power of their private keys, and both of them, as you can see, both of them get a value which is the same. So they can use this particular value as a private key for their communications. You might ask that if Oscar can get this value G raised to power A mod P and G raised to power A mod P, and can't he just fetch the value of A? So this problem is called discrete logarithm problem, and it is proved to be not trivially easy to solve, and it needs at least a brute force attack or an attack known as baby step, giant step algorithm. All right. So, but consider this case that the connection between Alice and Bob is and he can just fetch these wires towards it. And when Alice sends the partial key, thinking that this partial key would go to Bob, it is received by Oscar instead, and he sends his own partial key. And instead of Alice and Bob making a connection, the connection is formed between Alice and Oscar and Bob. So this way, Oscar can impersonate as Bob for Alice and impersonate as Alice for Bob. So this way, he can just decrypt all the messages and pass it on to Oscar. Then Oscar messages, and he can just decrypt and just pass it on to Alice. So the answer to the question we started on is no. All right. So there's a concept called digital signatures. Digital signatures allow you to disclose a public key, a public value, just some numbers, which would then allow any third party to verify if the piece of information has been authenticated by you. These signatures work just similar to like what real signatures do. Like whenever you see a document that is signed by someone, you know that this is approved by that person. So this is the same concept for digital signature. So these are mathematically backed, and you cannot use just the public key to forge a new sign. So you cannot use my public key to make a new signature that make my signature, and you need my private key to forge these signatures. So we can use this signature this way. Uh, Alice might just disclose her public key to everyone and say that if you see any of these messages sent by my name signed with this public key can be used to verify, but it cannot be used to forge. So if the signature is correct, it is indeed me. So there's still a problem in this approach. Bob can still say himself to be Bob. I'm sorry. Oscar can still say that he is Bob instead of saying that he is Oscar. He can just impersonate as Bob again, and he can just tell everyone that I am Bob and this is Bob's public key. So how can we solve this problem? Mohit?
Yeah. So the problem that we're facing right now is, what if Bob can use his own private key to form a signature, which then other people are supposed to use to verify his identity. So what if we had a third-party organization doing these signatures for you? For example, if a third-party organization was to independently verify the identity of Bob and then sign his identity, like his name and his public key, then surely you can trust a third-party organization, and verifying this signature would make sure that you're talking to the right person. But the problem here arises when next slide, please. So the problem here arises when, what if okay, so first of all, this signature is called an SSL certificate. So an SSL certificate for a website is basically just a document that contains the domain of that website, the issuer, which is the third party that signed this SSL certificate, the name of the domain owner, the expiry date of the certificate, and the public key of the domain owner. So this SSL certificate is signed by the issuer, and that serves as a proof of authenticity, which you can verify to make sure that you're talking to the right server. But the problem with this is, what if Bob was to go out and form his own company, which then hands out SSL certificates? So say Oscar could just found Oscar Industries, and then he could say, okay, I am Bob, here's my public key, and it has been verified by Oscar Industries, which is his company. And then you, and obviously the details would check out, and you would assume that the details that he sent you are legitimate. So in order to circumvent this, the what we do is not any body is not any body is authorized to hand out SSL certificates. SSL certificates, valid SSL certificates, can only be handed out by authorized certificate authorities or CAs. And well, what verifies a CA? Like, what's stopping Oscar from just going out and founding his own CA? And the way we do that is a CA has to be in turn verified by another CA, which is in turn verified by another CA, which forms a very long chain of trust that's very secure and really hard to break. And this chain of trust ends at a certificate which is directly trusted by your browser or your PC or your OS. And these are called the root certificates. And basically, this is what helps us mitigate man-in-the-middle attack. So Bob can now send his public key and an SSL certificate, an authentic SSL certificate, which you can verify to make sure. And Oscar is now cut out of the communications. That's going to be it from our side for this session, and we're open to questions.
Thank you so much. If there are any questions, please let us know.
Okay, so I don't think anyone has any questions. So I'll just share an interesting fact. Uh, so acat.iitr, which we usually visit, uh, so that is on HTTP. So basically, it does not have a valid certificate that it can show us, and we can verify that our information is securely being transferred. So uh, if someone does a man in the middle attack from so if someone is listening in between you and the college servers, they can find out your password. Uh, so I think that's it. And if anyone has any questions, you can drop them at chat.stslabs.co, or you can take messages on Facebook or email us, or anyway, we'll be there to answer them. So we are planning on having our next lecture on Thursday. We upload the upload this lecture, uh, I think preferably on YouTube, and we'll share the link, and you'll get the details for next lecture by tonight. So thanks everyone.
Thank you.